Hello wonderful person, this is Anton, and today we're going to be discussing a somewhat intriguing discovery of a very unusual white dwarf that seems to show direct evidence for what the scientists refer to as white dwarf crystallization, or essentially signs that this particular white dwarf is slowly turning into a massive crystal. And because it contains a lot of carbon on the inside, in the past press has actually compared this to a massive diamond, possibly similar to what you see right here. But that's of course just an artistic or even symbolic interpretation. In reality, crystallization inside these white dwarfs is a much more complex process. And so in this video, let's actually discuss a little bit more about this particular discovery, how all of this was discovered, and what this means for astronomy. But it's important to start with a bit of an overview, especially because our sun one day is most likely going to become something similar. So today we know that stars that are less than 8 solar masses in mass will not go supernova, and instead will end up expanding a lot, produce what's known as planetary nebula, the concept that you can learn more about in one of the videos in the description, and right in the middle, as you can see from this image, leave behind a white dwarf that's actually responsible for the ionization of the gas that creates these beautiful formations. And it just so happens that one of the closest stars to us, Sirius, contains one of the more interesting white dwarfs that you can see right there. We've discussed the system and what the scientists discovered here in one of the videos you can find in the description. But I guess here the question is, so what exactly is a white dwarf? I mean, in a nutshell. Anton, explain it to me like I'm 5. Well, it's basically a core remnant from a star that lost its outer shell. But because this is a stellar core, it's also extremely dense and contains a lot of material inside that's been squished by everything that used to exist above it. But it's a core that does not produce any more energy. And all of this extra pressure and extra density creates conditions where electrons start to create their own sort of ocean. But because electrons are particles that are not allowed to be in the same state in the same amount of space, they create a kind of a external pressure that we refer to as electron degeneracy. This prevents the white dwarf from collapsing even further and basically maintains its shape and its mass up until it reaches a kind of a limit. This limit is usually around 1.4 solar masses and is referred to as Chandrasekhar limit. When that limit is reached, that's when the star can no longer sustain itself and basically explodes in what's known as Type 1a supernova. The supernova that usually produce around the same amount of energy because they always explode around the same mass, which is often why they're used as a kind of a distance candle to measure distances to various faraway galaxies. But they have to get that mass from somewhere, and usually they basically steal it from one of their partners. But this doesn't always happen, and sometimes the white dwarf is really far away from the partner, kinda like in the system of Sirius, in which case that white dwarf is going to age and change its properties, because it's essentially cooling down over time. And so even though it starts extremely hot, because it used to be a core of a star, and it actually starts really hot, producing a lot of very bright white and blue light, over time it cools down, slowly becoming reddish, and eventually it's supposed to turn black. And so the ultimate fate for all white dwarfs and essentially all stars like our sun is to become some kind of a black dwarf, producing no more light. But that takes a really long time, possibly trillions and more likely quadrillions of years. The universe is only 14 billion years old, so today nobody expects to find any of these black dwarfs, simply because the universe is relatively young. Finding a black dwarf would be a huge deal and would most likely disprove a lot of modern cosmology, but because we haven't found any black dwarfs anywhere, at the moment it basically suggests that Big Bang most likely happened, and overall, the age of white dwarfs seems to actually imply that we have the age of the universe calculated more or less correct. But the main point is that these stars do evolve over time, and part of this evolution involves the process of crystallization, when some of the ions inside the white dwarf start to freeze and acquire a kind of a crystallized pattern. But as white dwarfs crystallize, they also release a little bit of energy, which basically implies that they can actually maintain their temperatures just a little bit longer. And so all of this unusual electron ocean on the inside starts to assume a kind of a permanent shape, with all of the complex elements inside eventually crystallizing into one single massive object. But the obvious question is it actually a diamond? The answer here is, well, not really. Mostly because diamonds, which is of course carbon, have a much lower density. Here we're talking about density that's like possibly 1,000 times lower. Whereas white dwarfs very likely contain a very different type of carbon, that most likely has very different properties that we can't even imagine. But I guess interestingly, this process of crystallization does not seem to take as long as turning into an actual black dwarf. Because it looks like we've discovered at least one star out there that definitely shows signs that it's being crystallized from the inside. A star system that we used to think contains 3 stars, this is a star system known as HD 190412, but that seems to contain another object that we've discovered very recently with the help of the iconic ESA's Gaia telescope. And more importantly, this telescope also allowed the scientists to extremely accurately determine the orbits and also determine the age of the system, with the system appearing to be pretty old. The 3 stars orbiting here appear to be about 7.3 billion years old, but the 4th star, the white dwarf, appears to be only 4.2 billion years old. And so there's actually an almost 4 billion year discrepancy. And though it's obviously possible the white dwarf came from somewhere else, based on the observed orbits and just based on the fact that it's very unlikely, the scientists believe that all of these stars were very likely formed around the same time. And the fact that the white dwarf appears much younger implies one thing. It actually implies that it produces way more heat than it should, with the heat extremely likely being produced by the process of crystallization. Or essentially, as the carbon and oxygen atoms inside this white dwarf stop moving around and start forming crystallized forms, they actually slowly release energy that heats up the white dwarf even more, allowing it to release just a little bit more heat than usual. And all of this is visible as a very specific color signature coming from the white dwarf. Something that has been theoretically predicted before, but something that has never been observed. As a matter of fact, there's even a paper predicting all of this back in the 60s. You can find that paper in the description below. And so crystallization inside this white dwarf is really the only way the scientists can explain a huge discrepancy in the age of these stars. But I guess more importantly, the fact that this particular star system is so close to us, and the fact that it's already crystallizing, producing the cooling delays as predicted by various models, implies that these objects must be really common. Or in other words, crystallizing white dwarfs probably exist all over the place, it's just this one is the first we've discovered so far. But here the scientists have also discovered a bit of a discrepancy, specifically a little bit more heat than predicted. They don't exactly know why this is happening, but they believe it's possibly because of the isotopes of neon, located inside the core of the white dwarf, with the isotope potentially producing a little bit more heat and thus delaying the cooling even more. In other words, the scientists did not actually expect to discover so much heating or so much delayed cooling, with the crystallization process being extremely efficient and potentially producing way more energy than expected. But because of the similarity to the famous Sirius system, the scientists now believe this is a pretty common phenomenon. So definitely a pretty exciting discovery, or a pretty exciting confirmation that crystallization does occur in white dwarfs after all. But this is obviously not the first and not the last unusual discovery from white dwarfs, and you can learn more about other ones in the description below. Thank you for watching, subscribe, share this with someone who wants to learn about space and sciences, come back tomorrow to learn something else, and maybe support this channel on Patreon by joining channel membership or by buying a Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.